Hi everyone, this video is going to be a review of first-order linear systems of ODEs. So all this material is stuff that you should remember from your MATC58 class, or 244 if you were at Mississauga or St. George. So we will be going relatively quickly and won't go into it in too much depth, but you are expected to be able to do all this. So first, we'll recall that you can convert higher-order ODEs into a system of first-order ODEs. So we can convert higher order ODEs into a system. ODEs into a system of first order ODEs. Okay, and so if we start with the nth derivative of x plus a n, this is a 1, x the n minus 1th derivative, plus a 2, x the n minus 2th derivative, all the way through a n minus 1, x dot, plus a n x is equal to g of t. Well, we can convert it by just setting a new set of variables. x1 is going to be equal to x, x2 is going to be equal to x dot, x3 is going to be equal to x double dot, and so on through xn, which is going to be equal to the n minus 1th derivative of x. And once you do this, you get a new system of n first-order linear equations. So you have x1 dot is equal to x2, so that's pretty obvious. X2 dot, let me write this here. X2 dot is equal to x3. X3 dot is, and this goes on, all the way down to xn minus 1 dot, which is going to be equal to xn. And then xn dot is going to be slightly different. It's going to be based on rearranging the original equation up here. So that's going to be equal to minus a1 xn minus a2 xn minus 1 minus, subtracting all the way down to a n minus 1 x2 minus a n x1 plus g of t. Okay, and we can rewrite this in matrix form, which is pretty standard. So let's rewrite this as dx dt is equal to ax plus g of t, where, of course, x is a column vector of each of our individual x1 through xn variables. A is going to be the companion matrix, which is going to have zeros on the diagonal, on most of the diagonal until the second to last row, 1 directly above the diagonal until the second to last row, and in the very last row we'll have minus an minus 1 all the way through minus, it's going to be a minus, minus a2 and minus a1, and zeros everywhere else. So zeros everywhere else. And g of t is going to be equal to column vector with zeros, except in the very last column where you have the little g of t. And let's go with a quick example of this while we're at it. So this example is going to be x double dot plus 4x dot plus 3x is equal to sine of t. Well, this can be converted into a system of first-order equations. So this is going to be converted into, let's see, x dot, x1 dot, x2 dot is equal to, well, what's our A matrix here? It's going to be 0, 1, minus 3, minus 4. And we have x1, x2, since that's our x vector, plus our g of t, which is going to be 0 and sine of t. And these linear systems can be solved. So let's see, solving linear systems. So if we have a linear system, dx dt is equal to ax. Well, I'm going to go ahead and give the explicit dependence on t here. A of t, x of t, since the coefficients can be dependent on t, plus g of t. Well, Len, so this is for any linear system of this form. So not just ones that arise from the companion matrix. So this is a companion matrix when you convert a higher order ODE into a system of first order ODEs. But this is solving linear systems in general, not just companion matrices. Not just systems arising from higher order ODEs. So when we're solving this is one of the things you learned in your B44 class. The general solution x of t can be decomposed into a homogeneous solution plus a particular solution. So where xh of t is equal to a of t, x of t, and xp of t is equal to let's xh, a of t, xp of t, plus g of t. So this is the homogeneous solution. Sorry, let me write this here. Homogeneous solution. And this here is the particular solution. And as with linear ODEs, you can create a set of fundamental solutions. So let's let phi 1 of t through phi n of t be linearly independent solutions to the homogeneous equation. When we have a fundamental matrix of solutions in this fundamental matrix of solutions, I'm going to use capital phi of t is just going to be the matrix that consists of each of these linearly independent solutions as a column vector. So this is an n by n matrix here. And so note that because these are linearly independent, we know that the determinant of phi of the fundamental matrix solutions is not equal to 0 because of linearly independence. So we have an inverse because of linear independence. So we have an inverse. And this has a solution. So this can be proven, and hopefully was proven in your B44 class. So we know that x of t is equal to phi of t times phi inverse of t naught times x naught plus phi of t times the integral from t naught to t of phi inverse of s g of s ds, where x of t naught is equal to x naught. Okay, and so this is one of the big theorems in your differential equations class. We're not going to prove this in this course. I just want to make sure you remember all of this. Of course, solving this in general is quite complicated, but in the case of constant coefficients, things are a lot easier, just like they are for higher order ODEs. And in fact, this will have very similar solution forms. So if we have dx dt is equal to, I'm going to solve the homogeneous version first, because for the inhomogeneous version, you can, of course, then just solve for the constants, solve for the particular solution and add it to a general set of solutions for the homogeneous equation. So this, where a is coefficients are aij, and our aij's are real. Okay, so we'll assume that all of our coefficients are real. So by Picard iteration, and using things like the Picard fixed point theorem, which we're not going to discuss in this course, but by using Picard iteration, we can find that x of t is equal to e to the at x naught, where we're defining the matrix exponential by the Taylor series. It is going to be equal to I plus at plus a squared times t squared over 2 factorial plus a cubed plus t cubed over 3 factorial all the way to infinity. So this is the sum from k equals 0 to infinity of a to the k times t to the k over k factorial. And of course, let's have x naught is going to be a column vector. So an n by 1 real vector. So let's go ahead and see an example of this. I'm going to do it in the super simple case where we have a diagonal matrix, 2 by 2 diagonal matrix. Let's say that, suppose A is equal to A11, 0, 0, A22. And let's have x naught be equal to, let's go ahead and use 2 variables. Let's use x and y, just to make life a little bit easier. A little x and a little y. So, well, then, it's pretty easy to see that e to the at is, since it's a diagonal matrix, taking a matrix powers is going to give powers of each of the entries on the diagonal. And by using the Taylor series, you can see that this is equal to e to the a11 t 0, 0, e to the a22t. So these, note here that the exponentials inside of the matrix aren't matrix exponentials anymore, they're just scalar exponentials. Well, then we have that x of t, the general solution to this homogeneous constant coefficient linear system of equations, is going to be equal to e to the at x naught, which of course is equal to multiplying that by x naught, so you end up getting e to the a11t times x naught, and e to the a22t times x naught. And often we write this out separately. So we write this out x naught e to the a11t times this eigenvector plus y naught e to the a22t times this other basis eigenvector. And in general, if you can find an eigendecomposition, you can find solutions. So in general, if can find eigendecomposition of A with n linearly independent eigenvectors, can find, oh, no, go away, solutions to ODE. And let's write that out explicitly in a couple different cases. So sometimes you can't necessarily find the basis of eigenvectors, and in that case you have slightly more complicated results. We're not going to discuss that in too much detail, but we are going to give you examples in dimension 2. But first, let's go ahead and write out the answer for n linearly independent eigenvectors. So let's let these be lambda 1 through lambda n be eigenvalues of A with linearly independent eigenvectors. Independent eigenvectors vi. Well, when x of t is equal to then for let me rewrite the question here. So x of t is equal to a of t x of t, x dot of t. We have solutions x of t is equal to the sum from I equal 1 to n of ci, so some constant, times vi, our eigenvector, e to the lambda I t. Okay, and for consider the case without n linearly independent eigenvectors for n equal to 2. And obviously in higher dimensions you get something similar, but since this is not an ODE class, we're not going to cover those in detail, and hopefully you recall those from your ODE class. But case 2, we're going to let n be equal to 2, and let's say that the two eigenvalues are the same. Lambda 1, lambda 2 is equal to lambda, but only one eigenvector. Obviously, if the eigenvalues are different, then you're going to have different eigenvectors. But so if they are the same, sometimes you have two different eigenvectors, but sometimes you only have one. Well, then it turns out that sort of like with the higher order differential equations, when you have repeated eigenvalues, you have a term that's te to the lambda t instead of just lambda t. Though writing this out explicitly is a little bit difficult, but first we have the easy solutions, c1 v1 e to the lambda t. Plus, we also have c2 times, and this is the slightly more complicated part, vt te to the lambda t plus pe to the lambda t, where v1 is the eigenvector. Actually, let me just write this with only one eigenvector, v1. So that's there, where p is a generalized eigenvector, which you should recall from, what is it, A22, or your linear algebra class. A generalized eigenvector, a minus lambda I times p is equal to v1. Okay, and so the important thing here is you have the same sort of behavior as you do with higher order ODEs with constant coefficients. You have solutions of the form t e to the lambda t instead of just the e to the lambda t's. We're not going to go into that in too much depth, but it's good for you to be aware of that. And case 3 isn't really completely separate from these other cases, but it's just a case where you have complex eigenvalues. Well, then you can rewrite them in terms of sines and cosines. So, and lambda 1 is equal to lambda 2, the complex conjugate of lambda 2. So, lambda 1 is equal to a plus ib, and lambda 2 is equal to a minus ib, where b is not equal to 0. So they're actually complex numbers. Well, then you can rewrite things. So then you can use case 1 and just write it out in exponentials, and you have a complex exponential. Or you can take that complex exponential and you can convert it into sines and cosines. So then we have x of t is equal to, I'm going to say alpha 1 and alpha 2 because I don't want to actually compute these right now. E to the at sine of bt plus, let's call this alpha 3 and alpha 4, e to the at cosine of bt. Okay, and note that there are actually only 2 degrees of freedom. 2 degrees of freedom, C1 and C2, despite alpha 1, alpha 2, alpha 3, and alpha 4 appearing above. And we can use Euler's equation to see this. And case 1. Okay, so that was a well-run review over a lot of the material that we covered in your differential equations and linear algebra classes earlier. Basically, when you have a first-order linear, you can convert a higher-order ODE into a system of first-order ODEs, and then once you have that, you can solve you can solve both those linear systems as well as general linear systems. And for constant coefficients, you end up getting similar behavior, and you end up using the matrix exponential. One of the things that's useful to note is that if you're looking over here, if the coefficients, so if the eigenvalues here, if all eigenvalues have negative real part, this goes to 0. So this is the same sort of behavior as you do. Basically, the eigenvalues here play the role of the roots of the characteristic equation. I mean, they are the roots of the characteristic equation of the associated polynomial, but with respect to the matrix. But anyway, so if all the eigenvalues have negative real part, then all the solutions limit to 0 in the same way. And so you can do the same kind of stability analysis that you did with just a single higher order ODE by looking at the eigenvalues if you have n linearly independent eigenvectors. And even if you don't have n linearly independent eigenvectors, in cases like this, you can still see the same thing. You just can't write out the solution as easily. Okay, so hopefully that is all clear. And in the next video, we'll be giving some conditions to help check whether or not all the eigenvalues have negative real part. So of course, you can use the Routh-Hurwitz criteria for the roots of the characteristic polynomial. Sometimes that's a little bit messy though, and in some cases, for the eigenvalues of a matrix, there are easier things to check, such as the Grascurin disk theorem, which we will cover in the next video. So I'll see you there. Bye.